Very generous. Thank you, Hadi. And you guys really made this happen. It's amazing. The participants have done an amazing job to make this an interesting conference. And then I get to speak right after my former postdoc, Sho. So he gave you all the definitions that I didn't plan to give you. So thank you very much, Sho, for doing that. This was an early idea for the Stinson mug. And then there was another early idea with squares, but that seemed too dark. And then there was an idea with a black background that didn't work with the mug. So this is a room frame of type 2 to the 6 found by Doug. But on the other side of your mug, there's a little puzzle. You have to figure out what's going on the other side of the mug. Now there was another candidate for the mug, another candidate picture for the mug that we didn't use because it's from a conference that only a couple of us, Jeff has already left, but a couple of us were at that conference, and it was a conference on crosswalks, emergency rooms, and health insurance. And in fact, Doug didn't even make it to the conference because he got hit in the crosswalk in Seattle, and there's his black eye. So that's a mug shot that we chose not to use. Okay, but he's all better now. He's all better now. For me today, Q-polynomial association schemes are places where you do design theory. Each family of Q-polynomial association schemes is a design theory. Okay, that's my weird viewpoint. Okay, so for me, each family of Q-polynomial association schemes is a design theory, and this is based on Delsart's thesis that Sho talked to you about in excellent coverage and very creative use in the last half hour. So it's just a different viewpoint. Usually there's a monster under the bed, but if your kid is a cookie, then it's different. Okay, so that's the viewpoint today. Okay, so example is the Johnson association scheme, which you heard about today in Trent's talk, and then also in I think in Melissa's talk there was the Kneser graphs. No, it was the other way around. So the Johnson schemes, we have a set of size V, take all the K subsets, that's going to be our ambient space, the collection of all K element subsets. And I want to think of a design as a very, very small sample of that big space that represents the space precisely in some sense, right? So the Wilson matrices, many of us know these incidence matrices between T sets and K sets. Delsart calls them Riemann matrices, which is just a mystery for me. And the association scheme just corresponds to this Bose-Messner algebra where we just take the product of each of these matrices with its transpose, and we get basically graphs on the collections of K sets. So notice that algebra, that span, contains the all ones matrix and it contains the identity matrix, and that's essentially the definition of a Bose-Messner algebra. Vector space of matrices closed under these two multiplications, commutative and containing these two things. So there are these posets, like the truncated Boolean lattice, that capture this design relationship in many of these instances. So for example, for the subsets of the set of size V, so this is the integers 1 up to V, for any subset, we identify S with a 0, 1 vector, that's the corresponding row of that Wilson matrix. And this map that sends a set to its cardinality from the Boolean lattice just maps it to the chain, and the chain is the Q-polynomial ordering on the eigenspaces that you saw in Sho's talk. Okay, so here's this eigenspaces, and a T design is exactly a 0, 1 vector that's orthogonal to these eigenspaces V1 up to Vt. Okay, that's Delsart theory. So the simplest example is the only one I can draw. So we have the truncated Boolean lattice on the left, and the cardinality maps elements of the poset to this elements in this chain, which is the Q-polynomial ordering on eigenspaces, and we don't need to worry about that. Okay, so this is how I want to view the design game. View it sort of as a quasi-randomness phenomenon. You have some adversary, and let me not pretend that there's any crypto here, although my crypto lab icon and my NSF icon, thank you to the NSF, my crypto icon and NSF icon got pushed off the bottom of the slide somehow. So imagine an adversary is asking you to sample uniformly from the k-sets. And the adversary is going to check and see if your probability distribution really is uniform on k-sets. But the adversary, all that she can do is watch t elements and write down how many times you get all of those t elements, how many times you get t minus 1, how many times your set is disjoint from that. She just writes down those statistics, and she wants to see if those statistics are exactly what they should be if you're choosing uniformly at random many samples from all the k-sets. And a t-design is exactly something that matches those statistics. That's my definition of a t-design. Okay, so in this situation, someone's asking you to sample uniformly at random from an incredibly large, highly symmetric space. So let's assume that any two elements in the space, there's a symmetry that swaps them. So any two k-sets, there's an element of the symmetric group that swaps them. That's a generously transitive permutation group. Whenever you have that kind of symmetry, you always have an association scheme. Whenever you have an element of the automorphism group that swaps any two elements, then you have an association scheme. Okay, so I'm lazy, and instead of sampling from the entire space, I'm going to sample from a much smaller space, the blocks of a design. And the adversary is watching to see if I'm playing fairly, and so she is just checking each sample and checking to see that it matches the statistics that she would see from the entire space. So, so the adversary has limited skills and wants to check these samples, counting occurrences of some feature such as intersections with a fixed t-set. Okay, so today, all I'm going to do is just give you just that much overview. That's as much basically of the t-designs I'm going to give you, except for one example. Okay, so this is today's cartoon. Calvin says, this is just a soundbite. It's entertainment. This is sensationalism. Fortunately, that's all I have the patience for today at the end of the conference. So, okay, so here the adversary has a fixed t-set, and she's just counting the cardinality of the intersection of all of my blocks as I choose blocks uniformly at random for my design. She's calculating the cardinality of the intersection, and she wants to see if that matches the distribution that she would have if I was choosing from the big ambient space from the association scheme. Okay, here's one design. Okay, biplane. You know, only finitely many biplanes are known, and no one knows if there are infinitely many biplanes. Okay, it's symmetric design with lambda equal 2 from Rudy's paper, and this is actually due to Noda, which talked quite a bit about Noda in the previous talk. So we take the symmetric difference of the first column and the fourth row, symmetric difference of the first column and the third row, first column and second row, and so on. And then, anybody, any comment on that? Yeah? Yeah, this is the mutation. There are 3 symmetric designs, 1662 designs, and this is the one with the smallest automorphism group, only 384 automorphisms instead of 11,540 automorphisms. And all you're doing is mutating. Here, you're taking here this block in the traditional, the well-known design would have these two elements right here, this white here and this white here, and then we're swapping them and then just swapping them back in the other. There's just these little mutations. So the 3 1662 designs all come from these little mutations from the obvious one. This is the only one that cannot be linked. So there are linked systems of symmetric designs corresponding to the Nordstrom-Robinson code. And Rudy classified all of the linked systems, and this is the only one of those 3 designs that can't be part of a linked system of symmetric designs. Okay, next space. Hamming space. Joe just talked to you about this. Orthogonal arrays are the Delsart T designs in the Hamming space. The automorphism group, the wreath product acts generously transitively, swapping any 2 elements. So therefore, you have an association scheme. What's the adversarial model of an orthogonal array? Okay, let's say n equals 4096, and I'm supposed to be generating random bit strings of length 4096, but instead I generate from a very small space because I know that my adversary is only looking at 40 of the bits. I don't know which 40, but my adversary is looking at 40 of the bits, and I want to convince her that I'm doing everything uniformly at random. That's exactly what a resilient function does, and Doug Stinson prove that the resilient function's equivalent to large sets of orthogonal arrays. And Derek told you on Tuesday how we use that to clean up a true random number generator based on jitter, phase jitter and ring oscillators. Example 3, the next design theory is subspace designs. Instead of k subsets of a V set, we say take k-dimensional subspaces of a V-dimensional finite vector space, and the group acts wonderfully transitively, so therefore you have an association scheme. Your adversary chooses a fixed t-dimensional subspace, and now I start generating k-spaces, and the adversary counts the dimension of the intersection, and I want that to match. For that t-space, I want that to match the probability distribution that they would have if I was choosing from the ambient space from the entire association scheme. And that's a vector subspace t design. And we've just started to find these. This planet is really behind other planets on finding subspace t designs. They're very hard, but this class of design theory is not very well studied. Even less studied is the Q analog of the Hamming scheme. What's the Q analog of an orthogonal array? Designs of linear transformations. So here's the Q analog. So the universe is the set of all linear transformations from a finite vector space fq to the n to fq to the m. The automorphism group is this point stabilizer in this p gamma l m plus n fq. And it acts distance transitively, so we know we have an association scheme. So the adversary chooses a fixed inside the domain fq to the n. The adversary chooses a fixed t space and a fixed linear transformation from there to the other side. And I want to make sure that that linear transformation is extendable in exactly lambda ways. The number of ways to choose to extend that to a linear transformation in my design is constant. So those are the t designs in this space. How many of us have actually found some? How many of us have actually looked for these things? Well, it turns out that this is a translation association scheme. You have an abelian group acting transitively on the vertices, so therefore you have duality, and there's a coding theory, and these are called Gaby-Doulin codes or rank metric codes. So Bill Cantor and I tried to find some examples that weren't linear. So for example, if m is equal to n, take all the n by n matrices of trace 0. That's an n-1 design. Take the things of trace 0 and then find another transversal that's disjoint from that transversal and make that sum equal to 0, you get an n-2 design. So when you get t very close to n, there are these easy examples. When t is small, you can have some nice examples. So there's an example of a 1 design right here of 2 by 3 matrices. You take any one space inside f2 cubed and any linear transformation to f2 squared. There's exactly one of these things, no, exactly 2 of these that extend that linear transformation. Now there are bounds on these things from the coding theory viewpoint, and I bet you we could beat those bounds if we compromised linearity and we allowed our designs, our orthogonal arrays, to not be linear codes. There's a crypto system based on this, but I think it's been broken. So again, this is a Delsart project on the bilinear form scheme. Next example. Okay, Jürgen Bierbrauer tells Doug and I, well, he told me in Auburn that there are these things called TMS nets, which Charlie had written about, and I read Charlie's short summary of what the thing is, and Jürgen said, find a linear programming bound for this, because as soon as you have an association scheme, you have a design theory, you have linear programming bounds, you have a Ray-Chowdhury-Wilson-Rao bound, you have all these tools. And so then Doug was on sabbatical, and he showed up in my office after talk to undergrads. We went to Homer's Greek restaurant for lunch in Winnipeg. We needed a problem to work on. And then Doug proved a theorem that afternoon. And the next morning, he sent me a manuscript. The very next morning, he sent me a manuscript with this beautiful Rao bound that showed up in the Canadian Math Bulletin. I had to retaliate and prove a theorem myself. So he had this beautiful idea, and I'll show it to you when I show you the eigenspaces of the association scheme. And we had a linear programming bound. And basically, it's a metric space, but the Metric doesn't give you the association scheme. You need to take a fission of that metric, and you get these Niederreiter-Rosenblum's Fossman metric. This has generated a lot of literature, but this is all because Doug saw this thing. So here's the definition. Okay, I'm going to define it in terms of Euclidean space. Okay, so we're working inside the unit cube or any kind of box in Euclidean space, and we want to do optimization or integration or simulation, and we want to sample uniformly from the space. But we'd like to say, okay, up to some finite precision, an adversary can only sample boxes called elementary intervals. So the adversary is sampling, the adversary is looking at something that's a product of intervals where it's a power of the base b, let's say a power of 2, 1 over a power of 2 to the next number over that power of 2 in each dimension. And we want to make sure that when the adversary watches that and we choose our samples, that they're going to see the same exact frequency that they would see if we were sampling from the entire cube uniformly at random. And this should always work as long as the elementary interval, that box that the adversary is choosing from, is the volume is bounded below by b to the minus t. And that's a t design in this association scheme, and apparently very useful in financial industry and other areas. Vladimir Levenstein told me some cryptic phrase. He said, this is used for nuclear cosmos testing. I still don't understand that. But Doug and I had 2 papers, Canadian Math Bulletin and the Canadian Journal of Mathematics, on this, and there's a lot more to explore here. A beautiful thesis by Perkayastha at University of Maryland. So here's what the eigenspaces look like. Now they're not linearly ordered, like in the Q polynomial case. This is not a Q polynomial association scheme. In fact, somebody in the thesis wrote, I can prove that there are no McWilliams transforms for these codes because they didn't understand that the thing is not linear anymore. It's a poset. And so Doug was, in his row bound, he was grabbing sets of columns of the orthogonal array in these sort of groups, 2 from the first coordinate, 1 from the second, 1 from the third coordinate, and so on. And so Doug was grabbing them in these very clever ways, and those are exactly the eigenspaces of the association scheme. So there's a trivial eigenspace at the bottom, first eigenspace, and then it becomes nonlinear, and then that's the last eigenspace. And each of these things corresponds to collections of points in the cube. So for example, this one right over here consists of all points in 3 space up to 2 digits of binary accuracy that begin 0.01 and then something in the second coordinate, something in the third coordinate. That's what this means. Things above it are things that begin 0.01 in some other coordinate, they're completely free, and in the other coordinate, the first bit is specified. So that's what these diagrams, these little Farrer's diagrams correspond to these elementary intervals, these chunks of the cube. Okay, next example, the symmetric group. So the symmetric group, every group forms an association scheme. Take the center of the group algebra. The symmetric group is particularly interesting because we have lambda transitive and sets of groups, and you have t transitive groups, except when t is bigger than 5, the only t transitive groups we have are the alternating symmetric group. But you can find t transitive sets of permutations that aren't groups, and those are Delsart t designs in that particular association scheme. So the Journal of London Math Society, Bruce Sagan and I proved that if in dominance order mu is below lambda, then as soon as d is lambda transitive, it's also mu transitive. And we also proved, now this is a challenge for you, we proved that you can make the size of the design arbitrarily small relative to n factorial. But I think we use a result of Bierbrauer on that. Because inside this, some special cases are perpendicular arrays, authentication perpendicular arrays are some special cases. But I think that finding lambda transitive sets of permutations, that is, you take the shape lambda, the Farrer's diagram, you chop n points up into some partition of shape lambda, or another partition of shape lambda, and you want exactly, we need another letter other than lambda, you want exactly s permutations that setwise take these to these. That's a design in that association scheme. And this is also in today's cartoons. So it's just, this is where he works, okay? So for example, Latin square is a one transitive set of permutations, right? It's not a group, but if my adversary is watching any column and says, okay, in these permutations, column 3 is mapped to 2, 3, 6, 1, 5, 4. It looks like I'm choosing permutations uniformly at random. If my adversary can only watch one column at a time, it looks like that I'm choosing permutations uniformly at random. So how am I doing on time? My time is up. Okay, so T transitive implies T homogeneous. Livingston-Wagner proved this, and then Bill Cantor classified all the T homogeneous groups that are not T transitive. This is our definition of lambda transitive. I'm going to skip that. General situation now, we have some kind of poset sitting underneath our association scheme is at the top. We have this poset like the truncated Boolean lattice below. And then there's another partial order on the eigenspaces. And there's a map that maps every element of the poset to its corresponding eigenspace. And a T design should have this property that if I specify this collection of eigenspaces T and its preimage over here, then everything over here has to be covered exactly lambda times. And so this is the general setting that captured all of those. I said that we had dominance order. There's the eigenspaces for the symmetric group. That's the ordering, and these crime parameters that Shou talked about. We need to know how these crime parameters vanish in order to adapt the Rao bound, the Ray-Chowdhury-Wilson bound to these different situations. Okay, now we can take products of association schemes. We can take products of Hamming with Hamming schemes. And then you get split orthogonal arrays, mixed level orthogonal arrays. A guy named Jeff Wu asked me a long time ago to come up with a linear programming bound for mixed level orthogonal arrays. And when I did, I wrote to an expert. And the expert said, oh, I just got the same result last week. So I credited him in my paper, and he didn't mention me in his paper. Okay, and split orthogonal arrays, Levenstein's work, and Doug really got me thinking about this when he wrote these things about resilient functions. And then Johnson versus cross-Johnson scheme, you get mixed designs. And I want to talk to you about that because the Fisher bound for two designs is number of blocks is number of points minus 1. And we have a whole bunch of very small open problems there on mixed block designs. Hamming versus Johnson, a special case is room squares or room cubes. Or room cubes. Steiner tableaus of Bailyn and Messner. And okay, a little bit of time. So here's the 4 cube against Johnson 7-3, you know, where the final plane lives. So we take those two association schemes. In the product scheme, the eigenspaces fall into this poset now. Now the eigenspaces look like this, and I specify some collection of eigenspaces, let's say this one, and this one, and I say, okay, I need to be balanced with respect to those parameters. And that gives me a design theory problem. So you can just invent design theory challenges. It's the motivation is to find things that are either mathematically beautiful or have some application. Okay, so for example, for a room square. So now you've got pairs in the Johnson world, and you've got a two-dimensional Hamming scheme with some alphabet. Right, in this case, the alphabet has size 7. So these eigenspaces correspond to pairs, singles, nothing, rows of the array, cells of the array, and then here's rows and singles. And so a room square has to be balanced with respect to all of those green dots. Okay, so that means it has to, every pair has to occur in exactly one position. Every symbol has to occur some constant number of times in the entire array, of course. There's nothing at the trivial eigenspace. Every row contains some constant number of pairs. We don't require that every cell be filled, so that's not in our design, but we require that in every row, every symbol has to occur exactly once. So that's the association scheme definition of a room square. Now, you don't have to stick with the two-dimensional object. You can go to room cubes. And you don't have to stick with pairs. You can stick K-sets inside the cubes. And then you have Kramer's 7x7 by 7 Steiner cube that Spiro showed to me. So here you have these Kirkman triple systems, STS9s, that show up every slice in every direction. You get an STS9. These large sets are decomposed in these different ways. I don't know other examples of these things. I'd love to see more examples. I promised Doug that I would find one, but I didn't find it on the computer in time. I'll leave this up for 10 seconds. These are the open parameter sets, but I'm out of time. So I'll just let you grab a screenshot if you're online, or you can look at the talk afterwards. I was going to tell you that there's an application of the symmetric group thing to synchronization of automata. So this is Cameron and co-authors, and they look at the full transformation semigroup, and synchronizing automata shows up in terms of the semigroup that's generated by these things, the Cherney conjecture. There's a solution. Oh, I don't want to show you the solution to the puzzle. Thank you for your time. Okay. So I had closing remarks. Since I'm the last speaker, it's my honor to thank you all for coming. And what I wrote was, we have just finished. I think I have a microphone. Is this working? Yeah. We've just finished an impressive week of, I calculated 9 times 60 plus 26 times 30, 22 hours of lectures, medal presentations to 2 amazing mathematicians, a tribute to a great Canadian math researcher who has left us, a banquet and many dinners and breaks together. The Fields Institute provided us so much and really, really helped us. Facilities wonderfully optimized for the mathematical collaboration, excellent food, an unusually delicious coffee. Drinkable coffee is an unusual thing at conferences, very nice. Incredibly smooth and advanced technical support and equipment, and essential funding. And they provided us with Shu Cheng Kuo, who made it all seamless and took the burden off the rest of us so we could focus on the math. And Shane deserves thanks also, but let's thank both of them right now. I also want to thank our other sponsors for this generous financial support. In addition to the Fields, the US National Science Foundation, Microsoft Research, the Tut Institute for Mathematics and Computing, the Cybersecurity and Privacy Institute at the University of Waterloo, the Institute for Quantum Computing at the University of Waterloo, the Institute of Combinatorics and its Applications, PIMS, the Pacific Institute for Mathematical Sciences, ARMS, the Atlantic Association for Research in the Mathematical Sciences, and Worcester Polytechnic Institute. This funding is essential to keep mathematics going and for us to discover all the great things that you folks found this week. And of course, we want to thank all the great speakers and the participants for coming. Please submit your good papers to the volume. Send these to Charlie or Jeff by September. The deadline is roughly end of September. Okay, we want to get a good, strong volume. Our organizing committee has worked hard on this for over 2 years now. So I want to mention Peter Dukes. Can you stand up? Peter Dukes, Hadi Karagani, Adi Mashitan, please stand up, please. Lucia Mora, Brett Stevens. Brett, stand up wherever you are. Ruth Zong Wei, and myself. This is the organizing committee, and they did a great job. So we got some time still. Please stick around, talk to your collaborators, have a safe trip home, write to us with your testimonials. I'm getting there. Write to us with your testimonials. What did you get out of the meeting? Did you discover something? Did you start a new collaboration? Did you make progress on a paper with a co-author? What was your favorite part? These sorts of examples of testimonials help us with funding agencies. And we always have to do this with conferences to explain to the funding agencies how incredibly valuable these things are. And finally, happy birthday to Doug.
No. He's going to sing happy birthday, so the rest are also going to follow him.
Oh, maybe you could start that. I am Tone. Birthday to you. Happy birthday to you. Happy birthday, dear Doug. Happy birthday.